The algorithm that you can see playing on the screen right now is called shell sort, named after computer scientist Donald Shell. And what you can see also is that we are already sorting a pretty big array. It has a staggering 500 elements in it. Yet shell sort doesn't really seem to have any major problems sorting this array. So what is the secret behind shell sort? A recurring theme in our series on sorting algorithms were these turtles, that is, these annoying small array elements towards the end of the array. And most of the time, it is these elements that dramatically slow down our sorting processes. Sometime earlier in our series, we also came across an algorithm called comb sort. It worked just like plain vanilla bubble sort, but it introduced a gap between the two array elements that are compared at every instance in time. This gap was first rather large, and then throughout the sorting process it shrank. This little trick made sure that the algorithm took care of the turtles in an early stage of the sorting process, such that these array elements would not become the problem that they typically become later on in the sorting process. Now let's think about our most recent sorting algorithm, which was insertion sort. Can we do something similar here as well? As it turns out, yeah, we can copy-paste the gap idea from comb sort and use it for insertion sort too. The resulting algorithm is shell sort. But how should we choose the size of the gaps throughout the sorting process? Donald Shell initially proposed the following scheme. First, set the gap size to n over 2, then n over 4, then n over 8, and so on, until after a couple of iterations, you are comparing elements that are directly adjacent to one another. Is this the only possible sequence of gaps? Certainly not. The scientific literature has in fact produced a large variety of alternative gap sequences, each of which has their own pros and cons, which mostly depend on the properties of the array that we are sorting. Now, because of its great similarity to regular insertion sort, coding shell sort is not terribly hard. It's not very hard to code this algorithm. So instead of looking at a detailed numerical example in this video, I will instead walk you through some of the different gap sequences that are used with shell sort and spend a little less time on, the numerical example and the coding part, because that's pretty easy. So I'm going to focus on the gap sequencing here, because this is why shell sort gets to be so fast. Okay, so I am now in a new script called shell.py. And here I just quickly summarized that shell sort works just like regular insertion sort, but with this notion of a gap. And the gap size, the size of this gap, is determined by a specific gap sequence, which is determined independently from the actual sorting process. So this is a separate thing that we can code as a standalone thing, and only then do we have to care about embedding this in our insertion sort algorithm. And yeah, there are different gap sequences available. And the one that you already learned about in the intro section of the video was the shell gap sequence, which starts at n over 2, then goes to n over 4, and then n over 8, until eventually it reaches 1. Now, how could we code this? Well, we'll have to define a function that has one input, and that is the size of the array n. And from this size of the array, this function will now return a list of integer values, which is then the shell gap sequence. So this is what we'll have to code. I'm going to start down here by defining this function. I'm going to call it shell gaps, and we'll have our one parameter here, which is n. And what we want to return is a list of integer values, and we'll call this list gaps. So we'll have to define this gaps list. There are different ways that we can do this. There's not one and only way of generating this sequence of numbers. But the way that I'm going to do it is I'll define two variables here. I'll have g, which is the current gap size, which at first will be n over 2. And notice that I'm using this double division operator here to make sure that we have a whole number, so we don't wind up with gaps like 55.3 or something. We want whole numbers. And then we have our sequence of all g's that we already had in the past. And this will just be called, well, gaps. And this is what we'll want to return. But at first, this is an empty list. And now we'll go into a little while loop, and we'll say while g is greater than 0. Okay? So remember, we are starting out at n over 2, and then we'll decrease this g, so we are going to be updating this. And of course, it cannot get arbitrarily small, so we'll have to make sure that g is greater than 0, okay? And then we'll say gaps.append g, so we are passing g, which is n over 2 right now, into this empty list. And then we'll say g is equal to g over 2. Now, once g is equal to 1, and we'll do this once more, let's see what that looks like. So let's say g is equal to 1, and then say g is equal to g over 2. What does that look like? Well, it returns 0, okay? So g is now 0. And once that happens, once this point is reached, then this while loop will terminate and we are returning gaps. So let's see whether that works. So print shell gaps, and let's put 100 into here. And yeah, we see it at first it's 50. Well, n over 2, 100 divided by 2, that's 50. Then it's 25, and then it's 12. So what's happening here is that, well, 25 divided by 2, technically that's 12.5. But here, remember, we are rounding down to make sure that we have whole numbers. We wind up at 12, and then it's 6, 3, and then the same logic as before with 25 and 12. We go down straight to 1, and then the algorithm terminates because the shells gaps sequence is complete. We don't have to go any further and add 0 here. Okay, so that's it for shell gaps. Let's go back up here. What else do we have? The next sequence is the Hibbard sequence. Now, the Hibbard sequence reads 1, 3, 7, 15, 31, 63, and so on. So you'll see that these numbers are in ascending order, and this will be infinitely large as n is converging to infinity. And therefore, we'll have to be using these numbers in reverse order. I mean, obviously, the gap size has to shrink. Otherwise, we are never going to have a perfectly sorted array in the very end. So we'll have to use that in reverse order. But how do we even get there? I mean, how do we generate this without this reverse order thing? How do we even generate this series of values? Well, I think a good way of thinking about this is, what if all of these values were reduced by 1? So the first value would be 1 minus 1, 0. The second one, 3 minus 1 is 2. Then comes 6. And here we have 14. And then we have 30. Now, is that getting us anywhere? I'd say no. This is not really helping us. So let's try something else. Let's try increasing all of the values by 1. I'm going to go back here. And I'm going to increase 1 by 1. So that is 2. 3 plus 1 is 4. 7 plus 1 is 8. 15 plus 1, I think you're now seeing a pattern here. This is just powers of 2, right? So 2, 4, 8, 16, 32, and 64, and so on. So the next one, you can guess that. That's going to be 128, 256, and so on. And yeah, this is easy to code, right? So let's use that fact to generate the Hibbard sequence. I'm going to go down here, and now we'll define our new function. I'm going to call that, you guessed it, Hibbard gaps. I'm going to set this parameter again. We're just going to call it n. And now we'll have g and our gaps. At first, I'm going to set this to 0. And I'm going to specify an empty list here for gaps, as before. But now what we'll have to keep track of, remember, is which power of 2 are we working with? I mean, okay, so down here we had 2, 4, 8, and so on, but we have to keep track of which of these i's we are. So I'm going to call this I, which is just the position in the sequence of all powers of 2. So I'm going to have another one here. I'm going to call this I, and at first I'm going to set that to 0 as well, I think. And now we'll start our loop, and this loop will generate now a sequence of g's, a sequence of gaps, and this will grow forever unless we're terminating it somewhere. And here I'm just going to set this to, once g is greater than n, there's no point in adding any more g's to the gaps. So we're only going to have this while loop while g is less than n. Okay, well, the first thing we'll do is we'll start with I. Right now, this is 0, so we don't want to have 2 to the power of 0, which is just 1. I mean, we could do that, but then again, it's not really, we have to add and subtract a little bit more down the road. So I'm going to start with 1 here, and this is 0 at first, and then I'm going to increase it to 1. So it's now 1. And now we have to multiply 2 a bunch of times, or like just raise it to the power straight ahead. And this is what we'll do. So we'll use the power operator here. In Python, this is the double asterisk. So single asterisk is just multiplying numbers. Double asterisk is raising numbers to a power. And then, let's just leave it at that for now. And let's append this to gaps. This is exactly what we had before. And now I'm going to return this. So return gaps. And let's see what that looks like. So print Hibbard's gaps and set this to 100. So 2, 4, 8, 16, 32, 64, 128. Yep, this is working. This is now powers of 2. So with that out of the way, what is the next step here? Well, if you go back up here, we see, okay, we have to just reduce these values by 1. So I'm going to go down here. I'm going to put it like this. So we're going to subtract 1 when we're computing the gap size. Let's run this once more, and now it reads 1, 3, 7, 15, 31, 63, and 127. And yep, that's really all we have to do to generate this sequence of values. So this is exactly the same now. Except, the values are the same, but we now have to put them in reverse order. Remember, we cannot start with a gap being equal to 1 and finish on a gap that is extremely large. So the only thing we'll have to do here next is to just type gaps.reverse, run this once more, and now, I did this while we were still in the while loop. We have to unindent this, so this has to be outside of the while loop. Just before we return, we could also do it like this, have it down here in the return statement, but generally I don't like this, so I'm going to have it as a separate line here, but you can also have it down here. Anyway, let's run this. And now it is just the way we need it to be. This is the Hibbard sequence. Okay, so next, let's have a look at the Papernov and Stasevich sequence. I don't really know how to pronounce this, but I think it's not too hard to code this, because if we look at it and compare it with the Hibbard sequence, we can see that this is not too different. So it now says 1, that's the same. Okay, but then 3, 5, 9, 17. And remember how we just had to change this into a 4 and this into an 8 and this into a 16 to generate a sequence of values that we can easily see the pattern where they come from. And let's try to do something similar down here. Now, what if this was a 4? And okay, this is not getting us anywhere. Let's, instead of increasing it by 1, let's decrease this 3 by 1. So this now becomes a 2. And then we'll have a 4 here. 5 minus 1 is 4. Then 8, and then 16. And voila, you see the same pattern. It's again just powers of 2, which are shifted by 1, okay? And yeah, so it's the same story, really. And we can easily code this by just taking our previous code and making one minor adjustment to it. So I'm just going to copy this down here. And I'm going to call this the Papernov-Stasevich gaps sequence. And yeah, instead of subtracting 1, let's add +1 here. And yeah, so I'm going to return, I'm just going to use both of these functions for a moment. So I'm going to make this 100, and then we'll print the Papernov-Stasevich gap sequence here also for n equal to 100. Let's run this, and let's go back up here. Does that look familiar? Well, Hibbard, well, we said, 137. That's obviously what we had before. But now let's have a look at the second one. It doesn't start at 1, so that's annoying. But other than that, it's 3, 5. So that works. 9, 17. Perfect. 33, 65, and so on. We have just implemented the sequence, except that we are missing 1. So I guess the easiest way to fix that is just, add 1 into the gaps list. So before we add the first G to that list, already have 1 in there. and then we just append to that. So that's really all we have to do here, I think. So if we run this, the second list here, which is the Papernov-Stasevich gap sequence, now has that 1 at the very end of the sequence. Remember, we just reversed the order. And yeah, that is the sequence. We implemented the next one.